All right. Hello, everyone. I'm David Chester. I'm a second-year master's student here at Duke University, and today I'll be presenting my portfolio presentation presented this past spring. The speed will be fairly similar to that of the original presentation, and the audience is primarily aimed at a trained statistician. However, hopefully this is entertaining to anybody who may be watching. All right. Let me share my screen. Okay. So the motivations for this project were twofold. The first was to learn survival analysis from a dynamic state-space modeling perspective. And the second was to practically enhance the private market investment process. With limited time, an investor needs to know which kinds of startups are more likely to get a second round of funding at any given point in a startup's life cycle after having had received the first round of funding. Given a majority of startups receive seed or venture as their first round of funding, this information might be of particular use to the modeler/investor. We're focused on using this binary static covariate, unchanging throughout time, and modeling how their respective coefficients do change throughout time. In simple terms, which kind of startup, originally seed-backed or venture-backed, is more likely to, one, instantaneously receive second round funding, i.e. the event at any point in time, conditional on having had not received funding up until that point in time, and two, which company type, seed-backed or venture-backed, is more likely to receive second round funding sooner than the other at any given point in time. We are further motivated by the fact that Cox survival estimates are global and do not incorporate this valuable dynamic information. And from a practical standpoint, investment firms are interested in knowing such time dynamics as it is often necessary to quote unquote court startups in the hopes of getting in on the next round of funding. The analysis provided by the survival DGLM framework sheds critical insight into these time dynamics so that the investor can better strategize when and on whom their limited resources are allocated. Okay. The data we used was from Crunchbase, which is a database for private companies. We use startups that began within the period from January 1, 2011 to January 1, 2012, where we map each company's starting point to a common T-naught. Our predictive survival functions are then overlaid with the Kaplan-Meier plots for the same period to explore model fit. We then overlay the predictive survival functions on the KM plots for the next window from February 1, 2012 to January 1, 2013 to illustrate predictive performance. We'll get to both of these plots later on in the presentation. We also know that nearly 60% of seed-backed and venture-backed firms never receive second round funding. Then preliminary EDA of the Kaplan-Meier plots indicate possible dynamic relationships as the survival plots cross circa 28 months. A standard Cox survival estimate provided a positive and insignificant estimate for venture-backed startups relative to the base level, i.e. relative to the seed-backed firms. And we find this analysis lacking in both significant outcomes and dynamic inference. So just zooming in, we see dynamic behavior at approximately 28 months and an insignificant estimate as well. We're hoping for quite a bit more. Okay. Lastly, there are other covariates, also static, such as company region, company market, initial funding raised, etc. These static covariates can also be evaluated through their dynamic coefficients throughout time. Furthermore, if we did have time-varying covariates, this model is flexible enough to incorporate them as well. The methods we used were consistent of a non-proportional semi-parametric hazard model with time-varying coefficients. Note that the Cox hazard model is proportional to the baseline hazard, which unfortunately presumes constant hazard throughout time. Here, we combine a piecewise exponential hazard function, factorizing the likelihood by time interval, while drawing on the general forward filtering backward sampling machinery of dynamic generalized linear models, which in turn utilizes simple random walk evolution with discounting, a modeling choice, linear Bayes estimation, and recursive and predictive sampling to obtain time-varying inference for the coefficients, along with uncertainty quantification for both the estimates and predictive survival functions. Note that in the poster, we are looking at the log hazard functions for seed-backed startups and venture-backed startups, and not at the time-varying coefficients themselves. The log hazard function is a more useful way of exploiting the time-varying inference of the coefficients as it provides the log instantaneous conditional probability of receiving second round funding at any given point in time. For clarity, note that the hazard for seed is this first equation, whereas for venture, we have this second equation. Note as well that we can extend this with more covariates, as mentioned earlier. And we also need to note that we have non-Gaussian errors. And since we have non-Gaussian errors, we can't engage in a fully analytic analysis. So we need to choose a conjugate prior with parameters based on the prior mean and variance of the partially specified prior information of the linear predictor. And then 2, use linear Bayes to update the moments of the state vector. Additionally, we note that retrospective smoothing draws on linear Bayes estimation. However, backwards sampling requires a fully specified distribution to simulate, whereas linear Bayes only requires mean vectors and variance matrices. Note as well that the DGLM framework presumes no distribution on the evolution errors. However, we make an assumption that an approximating normal is a maximum entropy variational based decision analysis strategy. And our assumption is fortified by the results of the model fit when we overlay the predictive survival function on the KM plot. And that's where we're going to go now. All right. So this should be fairly exciting. In terms of model fit, when we overlay the predictive survival functions on the KM plots, we see a direct match both with the median prediction and uncertainty intervals. This is of particular import since we obtain time-varying parametric inference, which we cannot get with Cox regression, but we still recover the non-parametric KM plot, which is our insurance policy, if you will. Then, in terms of inference, we note that the recursively sampled log hazards for seed-backed and venture-backed firms follow roughly similar dynamics. Rather, we see initial dips in the log instantaneous conditional probability of receiving second round funding. Then we see an uptick at roughly 4 months before a longer period of decaying probability of receiving second round funding. Despite similar dynamics, the hazard ratio clearly favors seed-backed firms early on, then favors venture-backed firms beyond roughly 15 months. This finding is subtle, yet absolutely critical. Any given investor might be under the impression that originally seed-backed or originally venture-backed firms are equally as likely to get funding at any given point in time, conditional on having had not received funding up until that point in time. And without plotting a ratio of hazard functions, this heuristic could be relatively understandable, especially since the individualized hazard function plots for seed-backed and venture-backed startups are so similar in quote-unquote pattern. However, when we plot the ratio of the hazard functions, we gain an essential insight. Despite the seemingly similar hazard functions, we see the ratio of the two treatments, seed-backed versus venture-backed, favors seed-backed firms with statistical significance through the first 10 months, while we see the relationship flip and become significant at roughly 24 months with a generally constant trend throughout. The ratio of survival functions largely corroborates these findings. We see seed-backed startups move faster to second round funding within the first 2 years with statistical significance up to the first roughly 20 months. Then see venture-backed companies become more likely to receive second round funding sooner, albeit with higher uncertainty and with statistical insignificance. So the practical takeaway is still investor dependent. One might want to spend time, quote unquote, courting seed-backed firms earlier on, then spend time, quote unquote, courting venture-backed startups later on. Or some might argue that strong competition requires investors to quote unquote court venture-backed firms from an earlier stage, say even from the start of the window. This analysis does not provide a blanket recommendation for investor behavior. This inference should, however, clearly be incorporated into any investor-specific strategy. One definitive take-home message is that investors should probably not focus on courting seed-backed firms later on, rather spend that time courting venture-backed firms, startups. All right, now. In terms of prediction, the overlays of the predictive survival functions on the KM plots of the next time window illustrate strong performance for most of the period. Then the predictive survival functions slightly overshoot the KM plots before undershooting for the last few months. Note as well that the second window had a high percentage of censored companies that entered the training data. All right. So with respect to the initial question, our time-varying inference of coefficients, seedback versus ventureback, clearly answered our question. We garnered dynamic statistical significance, whereas a simple Cox survival estimate was global, not dynamic, and insignificant. Furthermore, our model fit recovered the non-parametric KM plot despite being semi-parametric. Finally, we obtained strong out-of-sample predictive performance. So as mentioned, this model can incorporate other static covariates or time-varying covariates. The instance of using time-varying covariates is slightly more complicated when building the predictive survival function. One might think of simulating the future values of the time-varying covariates and then following suit. So in sum, this is where we would have been had we not had the machinery of the survival dynamic generalized linear model framework. And hopefully one can see we garnered quite a lot more with this more flexible dynamic machinery. And that is the end of my presentation, and I hope you enjoyed it.